All right. 17. Reflection, refraction. Section 1. How light behaves at a boundary. Let's get started. Okay, here we go. So, the law of reflection. So, anytime you have light striking a boundary in any way, it has to abide by the law of reflection, which essentially states that if you take a light ray and you shine it onto a smooth surface, a mirror, the angle of reflection is going to equal the angle of incidence. And the angle of reflection and the angle of incidence is the angle from the ray to the normal, in which the normal is the line perpendicular to the surface. So you see on this theta A or theta I and theta R, those are your angles of incidence and angles of reflection, and they must be the same. Okay. That is your law of reflection. So if you ever shine anything off of a surface, as long as it's a smooth surface, it's going to reflect off at the same angle in which it came in. So if you shine something in at 30 degrees, it's going to be bouncing off at 30 degrees. Nothing else. Nothing different. Okay, regular reflection basically is you have multiple beams of light hitting a surface. They bounce off that surface and come off at the same because the surface is so smooth and there's no change in it. Okay, so if they come in parallel, they're going to exit parallel because of the law of reflection. If 3 of them come in at 30 degrees, they're all going to exit at 30 degrees from that. Okay, in this image here, you can see that with the red, green, and blue rays that we have. Diffusion reflection, which happens all the time because nothing is a nice smooth surface, is when light rays hit a non-smooth surface. And so if you have it hit a non-smooth surface, the light kind of goes in multiple directions. So if you have light hitting, let's say, a rough wall, okay, it doesn't come up as, nice and smooth and looking. It's going to have, there'll be parts that there's still shadows in it, and there might be parts that are brighter than other parts, and that's diffusion. So because the wall's not perfectly smooth, they're going to hit wherever those rays hit the wall, that angle or that normal changes. It's not just going to be perpendicular straight up and down. As you see here, you've got 4 rays that hit, and there's 4 different normals. These dotted lines are all the normals, and you see they're all at different angles. And so the light coming off of it comes off at different angles. Okay, and that's your diffusion reflection. Optically dense. If you take light and you shine it onto something that has a different medium and it slows it down, it's known as optically dense. Okay, even though it might not be physically dense, it will be optically dense because it's slowing down light. And the more it slows down light, the more dense it is. Okay, so like easy one is from air to water. Water is more optically dense than air. Light travels slower through air or through water than it does through our atmosphere. Okay, refraction. Okay, so refraction is different from reflection. So reflection is happening basically on the outside of an object. So it's hitting off of an object and then continuing on, and it stays in the same medium. Refraction is when it goes into an object and goes into a new medium. So easy example of this is that if you put something in a glass of water, or if you have an image on the back side of a glass, you see that it kind of gets warped a little bit. And that warping of it is the refraction, because light comes in, changes direction, and then when it comes back out, it changes directions again. So it's slightly changed. Okay. If you see this bottom one, you can see how the light has changed direction as it goes through. Through the 2 mediums. If the angle of incident is 0 degrees, basically meaning it's running in perpendicular to the object, then it's not going to refract at all. So if you put something in and then you look at the light rays that go straight into it, it's not going to change because you need that angle of incident to give you an angle to change. Okay, in which we talk about with like Snell's law. So like if this one down here had come in at perpendicular to it, it's just going to go straight through. I mean, it makes sense. If it goes in straight, it should end straight. But if you have this light ray going at an angle, it changes its direction both times, when it goes into the object and when it goes out of the object. Okay. Light in glass. So if when it is when you shine light onto a glass or anything, not all of it will be refracted through. Okay, some will be reflected back. So like if you shine a light on a glass, you know, it kind of bounces back at you because not all of it has gone through. A lot of it will go through, but not all of it. Okay. And with this, some reflecting back, you can think of it this way. With some reflecting back, that's its energy, and so it slows it down. Okay, so it's slowed down with the amount of energy. So as it slows down, it wants to go back closer to the normal. It's getting pushed to the normal. So the slower it goes, the more it's going to hit that normal side. Okay. Snell's law is basically a formula. It is a formula in which, based on the density of the object, how much the angle bends. Okay, so the more dense of an object is, the smaller that angle is going to become. Okay, and it's just a quick ratio that they have. Okay, yeah, and that formula is the medium. N is the medium, so the medium of the angle of incident, or the medium of the incident, times the sine of the angle of incident is going to equal to the medium of the new object times the sine of the angle of refraction. If we're sitting in a vacuum, we can knock out Ni because Ni is 1 in a vacuum. That's the smallest that your medium can be. Okay, so if it's in a vacuum, you can say that the medium, the optical density, whatever, is equal to the sine of the incident angle over the sine of the refraction angle. Make sure your calculators are in degrees when you do this and not radians. Okay, so here's an example that we have. So we have an object that is going through a vacuum, and then it goes into water, and then it exits out of it. So starting from the bottom, it enters in at 60, and when it exits out, okay, when it enters in at 60, the angle that it comes outward is 40.6. So we would go sine of 60, the entrance angle, divided by the sine of 40.6, and that gets us our density of 1.3307. So that means water's the index of refraction is what it's called, is going to be about 1.33. Okay, and so that's kind of the ratio in which those angles change. So whatever the angle we pick, we can then use that to find the angle of refraction. Right, so now this question was asking at what angle is it hitting on the other side, so as it moves through, so that it exits at 60. So setting up, you have your medium of index or incidence. The sine of the angle of incidence, which is what we're trying to find, is equal to the density of the refraction times sine of the angle of refraction, which in this case would be 60. Calculate it through and you get 40 using an inverse sine as your function. All right, so here's some common incidents of refraction that you're going to use in some of the problems that you're going to get. So make sure you have these written down. So as you see, vacuum is the lowest you'll go. Air is just slightly higher. Water and ethanol, crown glass, quartz, flint glass, and then you see the highest one there is diamond. And so diamond would have the greatest change in that angle of incidence to angle of refraction. All right, so a light ray travels through air, is incident upon a sheet of crown glass, an angle of 30 degrees. What is the angle of incidence? Okay, so take a second, use Snell's law and the indexes from the previous slide to help you set this up and solve it and find your angle of reflection. So setting it up, we're in air, so it'd be 1.0003 sine of 30. The angle you hit into it is equal to crown glass, which on the previous slide says it's about 1.52 sine theta. Divide by 1.52, get you 0.329. Take the inverse sine of it, which means that the angle coming out on the other side would be about 19.21 degrees. All right, so let's talk about the speed of light and your incident of refraction. So the index of refraction tells you, how much objects are bending and everything, but it also can tell you how much light will slow down through that object. So the more dense of an object, the slower the speed of light will travel. Remember that the speed of light is 3 times 10 to the power of 8 meters per second. So let's say we wanted to, just slow it down, to cut it down in half. Okay, so it'd be 1.5 times 10 to the 8th meters per second squared. If we just wanted to cut it down in half, what would the index of refraction be? And that would be 2, because it would be 3 times 10 to the 8th all over 1.5 times 10 to the 8th, which reduced down gets you 2. Okay, so the the index of refraction basically tells you what rate you're decreasing the speed of light as it goes through the object. So the more dense an object is, the slower the speed of light is. So if you want the speed of light to go down to 30 meters per second, it's going to have to be a fairly large index. Now there's other things that come into play, like temperature and other things with it, but if we're keeping everything constant in this case. So the question is, what is the speed of light as it travels through water? Okay, so water's index of refraction is 1.33. So we'd go 1.33 is equal to 3 times 10 to the power of 8th, all over whatever the velocity is of water. Okay, and so from there we would solve it. So it's essentially just a proportion. 1.33 over 1 is equal to 3 times 10 to the 8th over v. Cross multiply, divide, and we end up getting our answer of the speed of light through water is 2.26 times 10 to the 8th meters per second. So it looks like it's a lot. Really, it's not. We cannot visually see that big of a difference. It's still traveling at the speed of light. All right. So that's the end of reflection, refraction, the first section of it. And we'll continue on, and when we talk about critical angles, and what if you shoot it at an angle and it doesn't refract, it doesn't go through the object, what happens?